Welcome all. In today's class, we will talk about the dimensional analysis. Before going to the dimensional analysis, first let us look at the basics definition and the basic parameters used in the dimensional analysis, and then we will see how to apply dimensional analysis to create a mathematical relation between to a given phenomena. So first we will see the definition of the dimensional analysis. As the definition says, it is a mathematical technique deals with the dimensions of the quantities involved in a process or phenomena. If I take a physical process or phenomena and if I want to create a mathematical relation for that to predict the behavior in future, then I have to go through the dimensional analysis. So that is a mathematical technique which deals with the dimensions of the quantities involved in the physical process. So what it does is it gives us a basic equation through which we can mathematically predict the future phenomena or mathematically predict the result of a phenomena. So before going to the dimensional analysis and how to see or how to apply that to a physical process, first we need to understand the quantities. So there are two types of quantities. The first one is the fundamental quantity or the primary quantity. So these are the quantities which are defined as the independent physical quantity that is not possible to express in another physical quantity. So these are like the pillars of the physics or pillars of the dimensions. So these quantities they are independent in nature and they cannot be expressed with the help of other quantities. So indivisible quantities, we call them as fundamental quantities, and there are 7 quantities which we can measure, and those some of them are length, which is denoted by capital L, then we have mass denoted by capital M, then time denoted by capital T, and temperature denoted by theta. So these are the physical fundamental quantities which we are going to use in our analysis purpose. Now let us see secondary quantities. The secondary quantities are the quantities which are derived from the fundamental quantities, which means to say that these quantities can be represented in terms of fundamental quantities. So they can be further divided, and they can be expressed in terms of fundamental quantities. So here the example, I will take the area. The unit of area is meter square. So area is given by length. A simple relation for area will be length into breadth. So the length has a fundamental dimension of length L. So I will write it as capital L, and breadth, again it is a measure of length. So it also has a fundamental quantity of capital L. So this area has a secondary quantity which is represented in terms of fundamental quantities as L square. Now I will take force. Force is given by mass into acceleration. Acceleration is nothing but rate of change of velocity or change in velocity by time, and the velocity can be represented as displacement by time. So I can write velocity by time as distance by time square. So mass has a fundamental dimension of m, and distance has L, and time has t. Since it is we have time square here, it becomes t square, and since it is in denominator, it is represented as t to the power of minus 2. So these are the secondary quantities which we are going to use in our analysis. Then we have to see the dimensional homogeneity. So if I have an equation and if I have to tell that the equation is dimensionally homogeneous, then it means to say that the right hand side and the left hand side of the equation has the same powers for the fundamental dimensions present in that term. So it can be stated as the dimensional homogeneity means the dimensions of each term in an equation on both sides are equal. To give you an example, here we have discharge. Discharge is nothing but the flow rate, and that is given by area into velocity. Here the left hand side we have discharge, which has a unit of meter cube per second, and if I write this in terms of fundamental quantities, then I can write it as L cube into t to the power of minus 1. Now I will take the right hand side, we have area into velocity. So area into velocity, area has a unit of meter square and velocity has a unit of meter per second. Again, so here we have in the numerator meter square into meter, which means meter cube divided by second. So it has a fundamental dimension of L cube t to the power of minus 1. Another example is velocity equation, which is given by root of 2gh. On the left hand side we have velocity, which is equal to meter per second, and it can be written as L t to the power of minus 1. On the right hand side we have root of 2gh. 2 is a numerical constant, so it doesn't have any units. G is acceleration due to gravity, which has a unit of meter per second square, and h is the height or head of the fluid, so it has a unit of meter. So here we have meter square divided by second square, and we have root. So root of meter square by second square will be meter per second, which has a fundamental dimension of L into t to the power of minus 1. We will be using these fundamental dimension terms for a physical quantity or a physical phenomena to provide a mathematical relation for that process or phenomena. Now we will see the methods of dimensional analysis. So the first and the easiest method is the Rayleigh's method, and the second method we are going to study is Buckingham's Pi Theorem. First, let us see how to apply the Rayleigh's method to derive a relation between the parameters involved in a physical process. So first, I'll give you the brief introduction to Rayleigh's method, then we will see a simple problem where we are going to apply the Rayleigh's method. So in the Rayleigh's method, this method is convenient. This is based on dimensional homogeneity, the principle of dimensional homogeneity, and this method is applicable when you have very less number of parameters involved in a process, maybe 4 or 5 parameters. If they are involved in the process, then this method can be used to provide a mathematical relation between the parameters involved in a physical process, so that we can predict what happens when a parameter changes, or we can find out a particular dimension, a particular property of the process. So here I'll take y is equal to f of x1, x2, x3 up to xn, and this can be written in the form of k into x1 to the power of a, x2 to the power of b, x3 to the power of c, and so on. So in the Rayleigh's method, we have a parameter, this y, we call it as dependent variable because it depends on x1, x2, x3, and these parameters x1, x2 and x3, we call them as independent variables, because whether the changes in x1 will not affect the changes in x2, or the changes happens in x2 will not affect x1 and x3, so on. So if x2 or x3 or x1 changes, then the value of y will change. So we call this as dependent variable, y as a dependent variable, and x1, x2, x3 and so on as independent variable. So when we know a process, and if we know all the parameters involved in it, and if you want to determine a particular parameter, then that can be taken as dependent variable, and the other parameters can be grouped as independent variables. So here y is a function of, that's why we have written y as a function of x1, x2, x3 up to xn. Okay, so this kind of relation can be expressed as k into x1 to the power of a, x2 to the power of b, x3 to the power of c and so on, with the help of Rayleigh's method, where k is a constant. So k doesn't have any dimensions on its own, it's a constant. And a, b, c, the exponents of x1, x2, x3 can be obtained with the help of the principle of dimensional homogeneity. So now let us see an example for this process or for this method. So here, using Rayleigh's method, we need to prove that the drag force Fd of a sphere exposed to uniform stream of a fluid is given by Fd equals rho v square d square into function of Re. Re represents Reynolds number, where rho is the density of the fluid, v is the velocity of the fluid stream, and d is the diameter of the sphere. Okay, this is the question. Now we need to prove that Fd is given by rho v square d square into function of Reynolds number. Since we know that Reynolds number is given by rho v d by mu, this is the equation for Reynolds number, which gives us an idea of how the flow is taking place in a given physical process. So let Fd is equal to, now I know that the drag force is a function of the fluid density rho, velocity of the fluid stream v, then the diameter of the sphere d, and Reynolds number, because that is given in the problem. Now I know that the drag force depends on those parameters. Now what I will do is I will write the dependent variable as a function of, that is k into the function's independent variables. So here let Fd will be equal to k into rho to the power of a, here x1 is taken as rho, then v to the power of b, then d to the power of c, and mu to the power of d, because these are the parameters which are present here. We have the fluid density rho, then velocity v, and diameter d, and in the Reynolds number I also have the dynamic viscosity mu. So I have written Fd as k into a constant into rho to the power of a, v to the power of b, d to the power of c, and mu to the power of d. Now I will write these in terms of fundamental dimensions. So the force is given by mass into acceleration, and acceleration is velocity by time, or change in velocity with respect to time. So mass into change in velocity divided by time. So velocity is again distance by time. So mass into distance by time square, that can be written as m into L into t to the power of minus 2, and k does not have any dimensions, it is a constant, so I will write it as k itself. Then rho, density is kg per meter cube, so kg is m, the fundamental dimension of mass is m, and for meter cube the length is L cube, so it is kg per meter cube, so m into L to the power of minus 3. Then we have velocity is meter per second, so length by time, L into t to the power of minus 1 whole to the power of b, because we have v to the power of b, then d to the power of c, d is diameter which is length, so L to the power of c, and mu, it has a fundamental dimension of m, L to the power of minus 1, t to the power of minus 1 whole to the power of d. So now to apply Rayleigh's method, we need to apply the principle of dimensional homogeneity. So if you want to apply the principle of dimensional homogeneity, then what we have to do is the indices of m, L, and t on both sides should be same. So on the left hand side and on the right hand side, the powers of m should be same, the power of L should be same, and the power of t should be same. So for m, I will consider the powers of m. For m, on the left hand side we have 1, m to the power of 1, so 1 will be equal to, on the right hand side here we have m, so m to the power of m to the power of 1 into a, so it is m to the power of a, so we have a, then here we do not have m, and this which is L, we do not have m, and when it comes to viscosity we have m to the power of 1 into d, so it is 1 equals a plus d. Now I will go to L. For the powers of L, on the left hand side it is L to the power of 1, so 1 will be equal to, here on the right hand side it is m L to the power of minus 3, so L to the power of minus 3 into a, so minus 3a, plus L to the power of b, so plus b, plus L to the power of, here we have c, so plus c, then here we have L to the power of minus d, so it becomes minus d. And for time t, so on the left hand side we have minus 2, t to the power of minus 2, on the right hand side here we have time, so it is t to the power of minus 1 into b, so minus b, and at the last term we have t to the power of minus 1 into d, so it is also minus d. When we simplify this, I will express all the terms in terms of d, all the other exponents, that is a, b, c, in terms of d. So when I do that, a can be rearranged as 1 minus d, and B from this can be rearranged as 2 minus D, and using the length equation, so C can be simplified as 2 minus D. So now initially we had written Fd is equal to K into rho to the power of A, V to the power of B, D to the power of C, and mu to the power of D. So in the place of A, B, C, I will substitute the value 1 minus D, 2 minus D, and 2 minus D. So Fd will be equal to K into rho to the power of 1 minus D, V to the power of 2 minus D, D to the power of 2 minus D, and mu to the power of D. So wherever I have D as a power, I will group it together. So Fd will be equal to rho minus D I have taken to the other, I have taken it separately, I have grouped it. Then V square into minus D, again I have taken here, it is in the denominator, and D square D to the power of minus 2D. So we have D square here and minus D is in the denominator. Then we have mu to the power of D, so mu here. So this I have grouped and have written it as a function of mu divided by rho Vd. So mu divided by rho Vd is nothing but inverse of Reynolds number. So I can say that Fd will be equal to rho into V square into D square into a function of Reynolds number. It's a function, whether it is directly proportional or indirectly proportional, we will get to that later, but it is just a function of Reynolds number. So that is how we apply Rayleigh's method, and this method is very simple, but it cannot be applied when you have very large number of variables or the parameters involved in the process. Maybe up to 4 or 5 parameters we can use this, but if it exceeds that, then you will get multiple groups like this, which will be inconvenient to solve. So we go for Buckingham's Pi theorem. The second method in the dimensional analysis is the Buckingham Pi theorem. So we will see this Buckingham Pi theorem with an application. So first let us see the statement of the Buckingham Pi theorem. The statement says that if there are n variables in a dimensional homogeneous equation, and if these variables contain m fundamental dimensions such as m, l, t, theta, etc., then they may be grouped into n minus m non-dimensional independent terms called as pi terms. So according to this law, so if we have a physical process or a phenomena, and if that has n number of variables including the dependent and independent variables, so these n variables has m number of fundamental dimensions, then we can group these variables into non-dimensional independent variables, which we call them as pi terms. So the number of pi terms will be equal to n minus m, that is the number of variables minus the number of fundamental dimensions present in that process or phenomena. Okay. Now we will see this. So there are several steps which has to be considered while solving or while applying a dimensional analysis by Buckingham's Pi theorem to any physical phenomena or process. For that, what we will do is we will go through an application of this dimensional analysis method to a turbo machine. Okay. Here we have the statement, the performance of a turbo machine depends on the following parameters. So it depends on the discharge Q, speed or RPM of the turbo machine N, size or diameter of the turbo machine D, then energy per unit mass flow rate, that is energy per unit mass flow is given as G into H, where H represents the head of the fluid in turbo machine and P is the power of the turbo machine, then density of the fluid rho, then dynamic viscosity of the fluid mu. Using dimensional analysis, we need to find out the relation between these parameters which affect the performance of a turbo machine. So we need to find a relation between the discharge, speed, diameter, energy per unit mass flow, power, density of the fluid, viscosity of the fluid in a turbo machine, which gives us how effectively or how easily the power or the other parameters affect each other. Okay. Now there are, I will count it here, we have 1, 2, 3, 4, 5, 6 and 7 parameters involved in this, and when you first and the foremost thing is to write the parameters or the variables in the fundamental dimension or fundamental quantities. This is because as we know that now I know there are 7 variables involved in this process. Now I need to find out the number of variables, number of fundamental dimensions which are present in this process. For that I need to write all the parameters in the fundamental quantities. So here I have listed all the 7 of them. So the discharge is meter cube per second. So as we know, meter has length L cube per second, so t to the power of -1. Then we have speed or RPM, rotations per minute. So the basic dimension of that will be rotations per second or rotations per time. So it is just t to the power of -1. Then we have the diameter, length, so capital L. Then we have GH. G is acceleration due to gravity, that is m divided by meter per second square, and h is the head, which is meter, so meter square per second square, L square t to the power of -2. Then we have power. Power is Newton per second, and Newton is joule per second. So if you further divide joule, it is kg meter per second square. So when you simplify that, you have m L to the power of 2 t to the power of -3. Then you have density rho kg per meter cube, so m L to the power of -3. Then you have viscosity kg per meter second, m L to the power of -1 t to the power of -1. Now we will look at the fundamental dimensions present here, and we will list out the fundamental dimensions which are present here are mass m, length L and time t. Only these 3 fundamental quantities are present in this in all these 7 parameters. So now let us list out all of them. So the fundamental dimensions which are present in this process are m, L and t. Only 3 are present. Now the number of fundamental dimensions, which is m, is equal to 3, and number of variables involved in this process n equals 7. So the number of pi terms will be equal to n minus m, which is equal to 7 minus 3, which is 4. So now these 7 parameters or variables can be grouped into 4 non-dimensional independent terms, which we call them as pi terms. So now the 7 parameters will be grouped into 4 non-dimensional groups, independent groups, which we call them as pi terms. So for that purpose, first we need to choose the repeating variables. Repeating variables are the variables which repeat in all the pi terms. So here I have taken diameter, speed and density as the repeating variables. So we have 3 basic rules for choosing the repeating variables. The first one is we should have one geometric dimension. So the geometric dimensions in a process may be the diameter of an engine, the length of an engine. So these are the basic dimensions, or these are the linear dimensions which can be taken. So here for linear dimension or the size, we have taken diameter. Then one should be the flow parameter. For the flow parameter, we have taken the speed of the engine n as the parameter, and the third should be the fluid parameter or the fluid property. For the case of fluid property, we have taken rho, that is density of the fluid, as the repeating variables. Now since we have 4 pi terms, so I will name them as pi 1, pi 2, pi 3 and pi 4, and I will write the equation as pi 1 will be equal to the repeating variables and their power are a1, b1 and c1, that is d to the power of a1, n to the power of b1, rho to the power of c1 into, now we are left with, since we have taken n, d and rho, so we have taken n, d and rho as the repeating variables. If we lay out those 3, then we have 4 non-repeating variables which are present. First one is the discharge, second one is the energy per unit mass flow, then we have the dynamic viscosity, and we have the power. These are the 4 variables which will not repeat in the pi terms. They are called non-repeating variables. Now for each pi term we need to choose one non-repeating variable. For the first one I have chosen Q, the discharge, as the non-repeating variable. So pi 1 will be equal to d to the power of a1 n to the power of b1 rho to the power of c1 into Q. The second pi term pi 2 will be equal to d to the power of a2 n to the power of b2 rho to the power of c2 and energy per unit mass flow, that is G into H. For the third pi term pi 3 will be equal to d to the power of a3. Again the repeating variables will be there in all the pi terms, d to the power of a3 n to the power of b3 rho to the power of c3, and I have taken power as the non-repeating variable for pi 3. For pi 4 it is d to the power of a4 n to the power of b4 rho to the power of c4 and mu, the dynamic viscosity. Now what we have to do is we need to take each pi term and we need to apply dimensional homogeneity to find out the value of a1, a2, a3, a4 and the other indices of the repeating variables. So once we get the value of a1, a2, a3 or b1, b2, b3 and b4, c1, c2, c3 and c4, then we will be able to express the pi terms or the relation between the parameters into 4 independent dimensionless groups. Okay, first I will consider the first pi term pi 1. So pi 1 is equal to d to the power of a1 n to the power of b1 rho to the power of c1 into Q. Now I will write this equation in the form of fundamental quantities. So pi 1 is a dimensionless, non-dimensional, independent term. So it has no dimensions. So I will write m to the power of 0, m to the power of 0 is 1, there won't be mass, L to the power of 0 is 1, there won't be length, or T to the power of 0 is 1, there won't be time parameter on the left hand side. So m, L and T to the power of 0 should be written on the left hand side, and that is equal to the fundamental quantities of the right hand side equations, right hand side terms, that is L to the power of a1, b to the power of minus t to the power of minus b1, m L to the power of minus 3 whole to the power of c1 and L to the power of 3 t to the power of minus 1, that is for discharge. Okay, now I need to equate the powers of m, L, t on both sides of the equation to get the value for a1, b1, c1. So for that first I will take the powers of m. So m on the left hand side it is 0, and on the right hand side we have only one term, the density term, so m to the power of c1. So 0 will be equal to c1, which in turns c1 is 0. Now I will take the length, the powers of length. On the left hand side it is 0, and on the right hand side we have a1 minus 3c1 plus 3. c1 is already 0, so a1 will be equal to minus 3. Then I will take the power of t. So 0 will be equal to minus b1 minus 1. So when I simplify I will get b1 is equal to minus 1. So now the term pi 1 can be written as, therefore pi 1 is given by d to the power of minus 3 n to the power of minus 1 rho to the power of 0 and into q, that is q divided by d cube into n. Now let us look at pi 2. The pi 2 is given by d to the power of a2 n to the power of b2 rho to the power of c2 into gh, that is m to the power of 0 L to the power of 0 t to the power of 0 will be equal to L to the power of a2 t to the power of minus b2 ml to the power of minus 3 whole to the power of c2 into L square t to the power of minus 2. So now again we need to equate the powers of m, L and t on both sides of the equation to get a dimensionally homogeneous equation. So now when we compare the powers of m on both sides, so 0 will be equal to c2 because m is present only in this term, so 0 will be equal to c2, which means to say that c2 is 0. When we compare the powers of L, so 0 will be equal to a2 minus 3c2 plus 2, which implies that a2 will be equal to minus 2 because c2 is 0, so a2 plus 2 will be equal to 0 or A2 will be equal to minus 2. When you compare the powers of t, so 0 will be equal to minus b2. Here we have t to the power of minus b2 and t to the power of minus 2, which implies that b2 is equal to, when b2 goes to the other side, b2 will be equal to minus 2. So now with this we can write pi 3 which is dn rho to the into gh, A2 is minus 2 and n to the power of b2 is again minus 2 and rho to the power of c2 is 0. So we get gh divided by n square d square, because both has minus 2, so both will come to the denominator. Now let us see pi 3. Pi 3 is given by d to the power of a3 n to the power of b3 rho to the power of c3 into power p. The dimensional form is m to the power of 0, l to the power of 0 and t to the power of 0 is equal to l to the power of a3, t to the power of minus b3, m l to the power of minus 3 whole to the power of c3 into m l square t to the power of minus 3. Again we will equate the powers of m, l and t on both sides of the equation to get a dimensionally homogeneous equation. So power of m is 0 will be equal to, here we have c3 plus 1. So c3 will be equal to minus 1. Then power of l, so 0 will be equal to a3 minus 3c3 plus 2. c3 is minus 1. So when I substitute that here, a0 will be equal to a3 plus 3 plus 2, that is a3 plus 5. So a3 will be equal to minus 5. Then the power of t, 0 will be equal to minus b3 minus 3. So b3 will be equal to minus 3. So the pi 3 can be written as d to the power of minus 5, n to the power of minus 3 and rho to the power of minus 1 into p, or pi 3 will be equal to p divided by d to the power of 5 n cube rho. Now the last pi term is pi 4, which is given by d to the power of a4 n to the power of b4 rho to the power of c4 into mu. The dimensional form is, the fundamental form is m to the power of 0, l to the power of 0 and t to the power of 0 will be equal to l to the power of a4, t to the power of minus b4, m l to the power of minus 3 into, or the whole to the power of c4 into m l to the power of minus 1, t to the power of minus 1. Again we will compare, or we will equate the powers of m, l and t on both sides. So we have the power of m, 0 will be equal to c4 plus 1. So c4 will be equal to minus 1. This is c4 is equal to minus 1. Then we have power of l, 0 will be equal to a4 minus 3c4 minus 1. So when you simplify, you will get a4 is equal to minus 2 and power of t, 0 will be equal to minus b4 minus 1. So b4 will be equal to minus 1. Now with this powers, the pi 4 can be written as d to the power of minus 2 n to the power of minus 1 rho to the power of minus 1 into mu, or it can be written as mu divided by rho n into d square.